Okay, so we continue last time. So last time we talked about discretization, and we discretized the continuous field before we had smooth field AAI X and EAI X, right? And then so these are smooth field. And then we have make a discretization, and by introducing a cubic lattice, what we call gamma, okay? And then I promised to define two kinds of discrete fields, discrete variables. So firstly is holonomy, and secondly I call gauge covariant flux. Right, and for all E edges of gamma, okay, edges of the graph gamma. Okay, so last time I have also, so these are the lattice variables. Lattice variables. So last time I have defined the holonomy. So this is called holonomy. H of E. This is the path ordered exponential and integrating the smooth field A, the connection field along the edge, right? And this is A is AI half tau I, and then E dot A. This E dot A is the tangent vector of the edge E. Okay, and last time I also introduced two useful formulas for computing holonomy. Computing holonomy from this gauge connection A, and there was a homework to ask you to check these two formulas are equivalent. Okay, so now we should introduce a, maybe it's good to write these two formulas. Sometimes I will use them. Okay, so first the formula one is H of E equals to identity matrix. So this H of E will be a 2x2 matrix. So well, because this tau I, this tau is just minus I multiply sigma. Sigma is Pauli matrix, a 2x2 matrix. So therefore, this holonomy is also 2x2 matrix. From 1 to infinity, 1 ds1, 2. N, and then A S1 N. Okay, so this is formula 1, and formula 2, this H of E is given by a limit infinity for delta S goes to 0. So 1 plus S1 A S yes. Okay, so here this in this formula, in the second formula, what we have done is just taking this edge. This is at E. At E, we divide infinitesimally into many small intervals, delta S1, delta S2, and so on. We infinitesimally divide this edge into small pieces, right? And then this limit is taking when n goes to infinity, when the number of pieces goes to infinity, right? And so here, this clearly this A of S belongs to the Lie algebra, SU2, and therefore this holonomy belongs to the group SU2. So 2x2 matrix belongs to the SU2 group. two-by-two unitary matrix of determinant 1. Okay, okay. And now, given the holonomy, so they are, you can immediately get some result. I will list them as a theorem. The theorem is that holonomy satisfy the following properties. Satisfies following properties. So firstly, so it is said that holonomy is actually a homomorphism from space of curves to gauge rule. Right? How we understand this? So given E1 and E2, okay, and then we connect these two edges. Okay, so this is E1 and this is E2. Okay, and then after we compose, so they are both oriented, and after we compose these two edges, we obtain a new edge which connecting E1 and E2, of course, and this is the new edge is called E1 composed with E2. Okay, and this is you can view this is kind of multiplication of curves. So this is, you can view this circle dot. It's a multiplication in the space of curves, right? And then by composing these two curves, holonomy is also, the holonomy of the new curve E1 circle E2 equals to HE1 and multiply HE2. Okay, so this is like product of curves, and here it is product in the group, product in the group. Okay, so here you can view mathematically as a relation between product of curves and product between group, and or you can just view that if you connect two curves, then the resulting holonomy on the longer curve is just the multiplication of holonomies on individual curves. Okay, so this is the first relation, and the second property is that holonomy also transform covariantly by if you reverse the direction of curve. So namely, suppose you have a curve E. Okay, so this is oriented in one direction. However, if you reverse this direction, right? So let me. So basically, this is the same curve, but now you reverse the direction, and this new curve, you can view this is also a new curve. So which means you change your parametrization of this curve by you call the previous 0 1 and you call the previous 1 0. Okay, so basically you reverse the parametrization of the curve, and then you get a new curve with the opposite orientation, what we call E inverse. This is just a name. We call it E inverse. Of course, it also looks like inverse. And then the holonomy transforms in a similar manner equals to HE inverse. Okay, so here this is the inverse of curve, and this is inverse of group. Okay, so here and from these two properties, you can see that holonomy, you can view this is kind of mapping by mapping from the space of curves to the group, right? And this mapping preserve properties of the product and inverse. So in the space of curve, you have operations like connecting curve as a kind of product, and you can also reverse the curve is kind of inverse. And then this holonomy, you can view this as a mapping from space of curve to the group, but this mapping preserve those mathematical structures. And that's why we say that from this property, well, in mathematical language, we can say that H is a homomorphism. Homomorphism from space of curves to gauge group. Yeah. Okay, so this is kind of mathematical description of these two properties. Yeah, but if you don't care about this mathematical language, you can just view this is just a property of holonomy by if you compose the curve, and also if you reverse the curve, and this holonomy, how this holonomy transforms. Okay, so this is first two properties, and the property 3 is that holonomy is a solution. So usually people define holonomy first. Here we define holonomy by this path order exponential, but in many literatures, people define holonomy by a solution of ordinary differential equation. So it is a solution of this of PDS. So this differential equation is usually called a parallel transportation equation. Equals to HS multiply A of S. Okay, this A of S is our previous A. This A equals to AI dot A half. Okay, so this is A as a function of S. And here, this H of S is an unknown, it's a matrix. Clearly, A is a 2x2 matrix, so H is also a 2x2 matrix. This is something we want to solve. Okay, and this is called a parallel transportation equation. Parallel transportation. Yeah. Okay, so yeah, so this is relates to parallel transportation defined by the gauge connection A. Okay, and the initial, this is ordinary differential equation. You need, if you want to solve, you need to set up the initial condition. So here you set up initial condition for H. H is something you want to solve. So H 0 when S equals to 0, it is identity matrix. Okay, and then you solve, and because this is first order ordinary differential equation, and with this initial condition, this is enough to uniquely determine the solution. So then you get the solution H of S. Then you can define HE, our holonomy, to be, or Wilson line to be H1, to be HS equals to 1. So this is how you get holonomy from differential equation. So this is property 3, and property 4, gauge transformation. Gauge transformation, okay, because holonomy is a function of gauge connection. Right? Holonomy is path order exponential of the gauge connection. So gauge connection has gauge transformation. It is not gauge invariant, so it transforms in certain way under gauge transformation. So here this is gauge connection. Well, so this is the gauge connection as a matrix, right? So well, remember our AA is AI tau half and half. So this AX transforms in this way, and the gauge transformation inverse minus partial A G X inverse. Okay, so this is the gauge transformation for A, and what you can derive then by plugging in this gauge transformation into the definition of holonomy, you can find that holonomy transform nicely and the gauge transform. So this is just like some conjugate. Okay. Can you see my voice clear? Hello? Hello?
I think there is some problem with the internet.
Oh, there's some problem of connection? Hello?
Yeah, you're kind of breaking out.
It's
We
breaking.
can see the image, we just can't hear you.
Yeah.
Oh, so you can't hear me. So now still the voice is not good enough. Hello?
Still didn't hear that.
All right. So point 4 is gauge transformation. The reason is that because H holonomy depend on gauge connection. Yeah, holonomy is defined as the path order exponential of a gauge connection. Yeah, so there's a gauge connection, and the gauge connection is not gauge invariant. It's transformed in a certain way. So here this is the gauge transformation for the gauge connection or gauge potential. Okay, and then according to this transformation, and you just need to plug this gauge transformation in the definition of holonomy, and you can derive the following gauge transformation for the holonomy, and you find it's transformed pretty nicely. The transformation is simple. It's very simple. So H of E and okay. By the way, I should emphasize that here this G of X, it is a SU2. So this is SU2 group valued function. So being gauge transformation, this is a group valued function. SU2 valued function on the spatial slice sigma. So which means at every point of sigma, you can get a gauge group. Yeah, you can get a group element G of X. For any X, you get a group element GX. Right, and so here you see that the gauge transformation of holonomy, it is just sandwiching this holonomy by two different group elements, and these are the group elements, the gauge transformation at S of E. So here S of E is the source. This is called the source of E. Source of E. So here you have an edge E, and this point, the begin point, this is called source of E, and the end point is called target of E. So here, this T of E is target of E. Okay, so you can see that the holonomy transform, the gauge transformation of holonomy only depend on the gauge transformation G at source of E and the gauge transformation G at the target of E, right? And so this is also right. So this is coming from general the gauge transformation for the smooth field. It is SU2 valued function, but the holonomy, because it's a discrete variable, the gauge transformation of holonomy only depend on the evaluation of this function at source of E and target of E. Okay, so you can see that this gauge transformation of holonomy is very simple. All right, maybe from here to relate something you might have heard in field theory, or if you're not, it's also fine. So you can see that suppose you have a closed loop. Although I mean here in our model, in our theory, we don't really consider. Well, current setup, we don't consider a closed loop on the lattice gamma. But suppose we go beyond our framework, we consider a closed loop. It is our curve E, okay, and then you consider the holonomy H of E, okay, and you can see that this here is just the target of E equals to the source of E, okay, and let's call this